All righty. Draw the axes for the HR diagram complete with labels that indicate what properties on each of the axes. So vertical axis is luminosity. And what you needed was high luminosity. So I'm just going to put 10 to the 6. That's a big number. Low luminosity, I'll put 10 to the minus 6. And these will be in units of solar luminosity. So you did not have to put that.
Okay.
Mira is sounding like, oh no. You needed to have high and low, or bright and dim, or something like that. Even though bright is technically not luminosity, no one would care here.
Does it have to be those exact numbers? Because I didn't.
No.
Okay.
You don't have to have any numbers.
Okay.
Just an indication of
indicating.
yes. This axis here is temperature. And the reason I make a big deal about which side is big and which side is small is because this side is like 30,000 kelvins, and this side's like 3,000 kelvins. And once again, the numbers, as far as we're concerned, they're not important in this context. They are important in an HR diagram, but not for the purposes of this quiz. So that's what we have for the first one, 8 points. So basically, you have the title, which direction is high. Not going to put which direction is low. For each of the axes, 2 points each. Okay, then the next one, identify what the following are. I saw some interesting variations on these. Number one, A, are bright supergiants. I saw one person that had super bright giants. I'm going to give them full credit, just for the record. But it's bright supergiants. And then 1B, just regular supergiants.
Blue and yellow giants.
2
I put blue and yellow giants.
for A and B.
Uh-huh.
Yeah.
2 is bright giants. Giants. 4 subgiants. Yes.
I failed this section so bad.
And 5.
What if we
Yeah.
described it? Would that we get some points there?
Oh my God.
I always look for ways to give you some points.
So if you write giants on
If you write giants on all of them, well, you're going to get full credit for 3.
Main sequence.
Mira, are we okay over here?
Oh, I'm okay. Oh, so often main sequence.
Okay, so that's 1 point for each. And then we have to show where they are. And this is the part where usually it's the hardest for people. First, that optimism. Good job.
Top one. Yeah.
There's our main sequence. All of the others are above this. I don't know why Mira's looking so worried. It's like, you got them right, okay?
What?
At least I think you did.
No.
Let me find Mira. No, I'm not going to grade it in front of everyone. Okay, wait. I did say she got them right. Let's see.
Oh my God.
I will not tell you if she got them wrong.
No, but if you don't say anything, then that.
As a general rule, this is just a vertical sequence. It's not exactly a vertical sequence, but as a general rule, one of the graphs we had just had lines like this.
Wow, I totally misinterpreted this thing. Well, I mean, I got those right. Those. Oh, that I grew up. This is a horrible quiz.
Another one of the HR diagrams had regions outlined, which is more useful. But this is the easier one for me to draw. So I could take, let's take all ones, because all one, you did a nice job here. Where's yours? And he just has them stacked there with the nice little things. Any questions about the quiz? Now, who was surprised to have the quiz today?
I'm not gonna lie. I guess I was also thrown off because of one of the diagrams has a little portion right underneath the main sequence.
Mm-hmm. What's that?
That has the white dwarfs on it.
Yes.
So that threw me off. So
yes, I was going to put those on there and then I took it off. White dwarves are down here. Brown dwarves would be down there.
You guys said blue giants and yellow giants, right?
Okay, so when I grade this, of course, like I said, I always trying to look to give you points. So you guys shouldn't have super low grades.
Not the best, but not low.
I'm looking for the best, okay? That's what I'm looking for. All right, let's go to the lecture, which as always will be totally fun. So what we're going to look at here, I don't know why it takes 2 clicks to get there, but it always does, is looking at what we believe are new formed stars and then how we make scientific explanations about how those came to be. So this here is a picture of, it says the Carina Nebula, a place where new stars are being formed. And now you look at this and there's lots of cool things to know. First, let's start with the nebula. What do you see when you look at that picture as far as the nebulae go? Okay, all one sees a cloud of gas. Where? Everywhere. Everywhere's a good answer. Let me circle a region here. What kind of stuff is that? In terms of the 3 names we had for nebulae. It's blue, so it's going to be, the name isn't blue. Why is it blue? Okay, close. It's called scattering. Refraction is bending when it goes from one medium into another. Scattering is bouncing off of things. Yeah. And so that's from scattering, Rayleigh scattering, the same reason our sky is blue. So this region here we would call a reflection nebula. And in terms of this chapter, we're like, who cares? Okay, what else do we see here? There are 3 types of nebulae. What else do we have? Okay, we've got the big dust cloud in the middle. This thing here. Okay, it's not a very good outline. I'm going to delete it in the end. That's a dark nebula. That's D-A-R-K. And that leaves this stuff here. What's the pink stuff? What do we call the pink nebulae? Emission. And the difference is emission and reflection nebulae, how close they are to a star and the angle you're viewing from. The dark nebula, though, that's a completely different thing. The dark nebula is the one that we don't shrug off. That's the one we're all excited about for this chapter's purposes. The dark nebula is very thick. Because it's so thick, it blocks ultraviolet light from coming through. And so it's nice and chill in there. And so you form molecular clouds. So you have molecular gas. The temperature is in the ballpark of 10 to 20 kelvins. 10 to 20 kelvins. How does that compare to room temperature? It's cold. It's really, 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 really cold. What's room temperature in kelvins? 300.
Oh, 300.
300 is room temperature kelvins. Well, 293. 300 to the nearest 100. So that is over 10 times, more like 15 times the temperature of room temperature. And it's really, really close to absolute zero. Really cold, which means the molecules are moving very slowly. Why is that interesting for us? That is where stars are formed.
The cold regions?
Yes, in these molecular clouds. So molecular cloud, do I have the word molecular cloud somewhere here so I can just... Doesn't have the word molecular cloud here. But in those molecular clouds, that's where stars are born. And so what do we have here to suggest that a star is being born? Well, we have things like this right here. What we have there where the hand is, you have a forming solar system. That is one, maybe a binary star, I don't know. But that is where you have a solar system forming. And you can see we have other things up at the top like that. So we have things that scientists have identified as these are pictures where we can see forming stars. So we're going to learn a little bit about that, but we look here and we see these cool things. Now, how thick do you suppose this nebula, this cloud is? Here's some other things that would be forming. Okay, thick, I meant density. Size, a few hundred light years. It's probably, if you take the entire size of this, it's probably maybe 10 light years. Which is a really big distance, right? I'm saying only 10. Yeah, it's a really big distance. But how thick is the gas here? Our textbook compares it to cirrus clouds. Would it be about the same density as the cirrus cloud that we have in our sky?
It doesn't look like it, but it's less dense.
That's right. It doesn't look like it, but it's less dense. Way less dense. Our textbook just says, but a much lower density. Because the average density in space is 1 atom per centimeter cubed. And here it might be 100 times that density, which is still virtually a vacuum. On Earth, we'd say, wow, there's nothing there. Okay, other pretty pictures. You guys have seen this pillars of creation, I'm guessing. Up until I started teaching astronomy, basically, the Orion Nebula was hands down the most exciting place to study star formation. And then the Hubble Space Telescope took this picture. And these are called the pillars of creation. Why pillars of creation? Because this is a region where we see what's predicted to be what goes on with the formation of stars. It's a big nursery for stars. It's in the Eagle Nebula. And so because this is in the Eagle Nebula, astronomers looked at this and they said, okay, let's look for places where we have forming solar systems, things like that. And they said, and you can see that's not the only one. There's another one here. There's another one here. You know, they're all over the place. Each one of those is a region where you have, they believe, a center where masses come together, and basically the cloud is retracted away, and now you can see that forming star. So they called these evaporating gaseous globules. Why did they call them that? Or gas globules? Because then it has an abbreviation of eggs. So they could say we found eggs in the Eagle Nebula. Because astronomers are some funny people. You can't deny this. So those are evaporating gas globules, which are nurseries for stars, we believe. So super exciting. What's the size here? If you read the text, it says that the distance from here to here is about 1 light year. Once again, a light year is a really big distance. So it's a really big structure out there. And that structure is, I forgot, something like 100,000 light years away or something like that. Where do you see it? Oh, yeah, 7,000 light years away. Okay. Now, how awesome is this? This is looking at the constellation Orion, Orion the Hunter. And you see there, we have the obvious star here, Betelgeuse, which is spelled something like that. The first 5 letters are definitely right. The next 2 may be in the opposite order. Always got to point out Betelgeuse and Rigel because they are very bright stars, one of them being a red giant, one of them being a blue one. But what do you see if you look at infrared? Something completely different. The visible light, you see those stars and it looks pretty clean. You look at the infrared and you see that this is all part of a big cloud. Now, that is false color. The infrared picture is false color. And you might ask, why don't they do it in true color? But then if you think about it, you realize that our eyes see true color, right? And infrared is below what our eyes can see. Hence, there is no such thing as true color for infrared because we can't see it. They make it true color infrared, it's just going to be black because you can't see it. So the false color there is indicating, and when they make maps of infrared or ultraviolet or radio, and they use false color, they will make the colors correspond to what they want to bring out. So the color may be varying on different things. So I don't think it says here what they use for the colors here. So yeah, it doesn't say what the colors are. I imagine that the more yellow we see, the more infrared radiation is being produced. And that would be a pretty reasonable way to choose your colors. So when you look at this, the entire Orion constellation has one big cloud of gas. And that gas cloud, I should hide this, not hit stop recording. That gas cloud extends, maybe this is where the 100,000 light years was. Really big cloud of gas. Did you have a question?
Yeah, I was going to say, so if you said that infrared we can't see it with our eyes,
Correct.
Then how do they know that it's there? Is it just through the waves that are...
Right. Infrared is wavelengths that are longer than red light. And so you can make a detector that can see infrared even though our eyes can't.
Okay.
That's what night vision goggles are all about. You're giving off infrared radiation. And so an animal that can see an infrared can see you when it's completely dark. And so the night vision goggles are cameras that can see infrared, and then it converts it into a false color visible picture for you to see. That's what this is as well. So we have something really interesting going on. Super bright here. That means we have a lot of gas that's hot gas. It's not cold. Cold gas would not be giving off much radiation. So we have a lot of hot gas there. And it's those hot gas clouds where all of the cool things happen in life. If we look at the constellation, here's an asterism. What's the name of this asterism right here? Orion's Belt. If it's clear tomorrow night, we should have a chance of seeing this if we stay out for longer than 20 minutes. Time changes this weekend, so next week you can start taking the lab final. Next week when we go out there, it's going to automatically be an hour later than it has been, and so we should have Orion starting to peak up, when we start lab next week, hopefully. So here's Orion's Belt. That's an asterism. This down here is part of Orion. Well, this shows the whole thing. Orion's sword hanging from his belt. And what's important about that sword is this region here. What's going on there? Well, many of us, I'm not going to ask because somebody might be embarrassed, but many of us grew up in Seventh-day Adventist culture, and you probably know that Ellen White talks about seeing heaven through, I believe it's through Orion. One of my predecessors at PUC, Pacific Union College, wrote a paper where he was analyzing that and saying, what the most likely thing is that she was looking at. And I think by general consensus, she's talking about here. So if you want to call it Seventh-day Adventist mythology or Seventh-day Adventist lore, says that heaven is beyond there. When we talked about Bernard 68 in class on Friday, you might remember me saying that when that was discovered, people said, look, if you go beyond there, you have a tunnel into heaven, maybe. A lot of people have come up with some interesting ideas about what we see out there. And I am certainly not here to make any case about that. How many people were at the well Saturday? We talked about creation, and I mentioned that when I look at astronomy, that's a place where I see the work of God. And I should probably clarify just a little bit. How is it that I see the work of God and things like this? Right, everything I'm talking about here seems to be conforming to man's interpretation, isn't it? But when I look at this, I see amazing intricacies of the laws of nature. And those intricacies of the laws of nature, to me, point to the intelligent designer who created these laws so that everything can occur, so that we have all of the amazing things out there. Okay, so what's going on in these regions? Lots of gas clouds. Let's look at them more carefully. So here's looking more carefully. This is the Orion Nebula in visible light and then in infrared radiation. The infrared, you can see a lot more detail of the gas clouds because they're the ones that are giving off lots of infrared radiation. So, wow. You can see a lot more detail in the picture in the textbook, or if you look on a computer screen than you can looking at the projector here. This picture is actually reasonably rich in detail, and you just don't have the contrast in the projection picture. It's actually a reasonably good projector. Yeah, if we close the blinds, we'd probably see some better. I turned off the light so we could see some better contrast as well. Anyway, so we look here, we see more detail. Going into the center of the Orion Nebula, you have this region here. What's the difference in these pictures? Once again, we have visible light and infrared. In the visible light, you have the clouds are blocking the light of most of the stars behind the cloud. In the infrared, you can see through the clouds, so you can see the stars that are behind. But those things that I circled are called the trapezium cluster. And one of the things that's really cool is you have lots of stars forming in this region. You have about, 20,000 or so stars being formed in this area? So let's talk about the process of star formation. This picture is showing a region in space where you have some old stars hanging out, some younger stars, and then you get to the molecular cloud and stars are currently being formed. How could this occur? Why is it that you have a sequence going from older stars and you just travel in a straight line, you get to younger and younger until you get to where stars are being formed? What would that suggest? There's something we've talked about with Hawaii that actually kind of relates to this. Go ahead.
Well, Hawaii is because the hot spot shifting to tectonic plate movements.
Yes. In Hawaii, now this is a completely different thing, but it's the same logic. In Hawaii, we have a hot spot, a place where magma comes up and punches through the surface of the earth. And then the surface of the earth moves over, and so as it moves, you have, here's where it's currently being built, older, oldest. We have that kind of sequence in the sky. And so we want to kind of use the same type of logic, even though it's not close to the same thing going on. So whatever is going on here must have in the past been here, and then further past here, and then further past here. It's not a hot spot, but the same logic. And so what's going on when a star forms? Well, think back to our solar nebula theory. We've already talked about how we believe the solar system formed. So you regurgitate for me, how do we believe the solar system itself formed? Started with the solar nebula, then what happened?
Like started going close together.
Okay, something made it compress. That something would be a shock wave. A wave of pressure came through, made things move closer together, and when they get close together, gravity takes over. So if that's how a star is formed, then we can look here and we say, okay, there's a whole bunch of protostars being formed in gas, which means whatever caused it must be passing this direction, and it's reached, okay, it's passing this direction, it's reached here now. So we have this cloud of gas, and by extension, the cloud of gas must have extended all the way back to here at some point in time. And a shock wave had to start, okay, where's my hand? There it is. Had to start here, and it's worked its way steadily this direction through the cloud of gas. And as the shock wave passed, stars formed in that region. When stars form, you're going to have, of course, matter falling in. But as matter falls in, you start up that nuclear engine. And that nuclear engine is going to be pushing stuff out, cosmic wind, right? And that cosmic wind, especially when the star is done forming and becomes a star, it's going to blow hard, and it's going to then recreate or continue on the shock wave that started. And then when stars die, young stars, very massive stars have short lives, and so they'll die fairly quickly, a million years or less after they're formed. And so when they die, they're going to have a big explosion that will continue the shock wave again. So the theory is that the shock wave is propagated because of star formation and death so that it keeps going. And as the shock wave passes, you have stars form, not just a single star. Our sun probably didn't form as a single star. We find stars in clusters of stars. Those clusters may have thousands or even millions of stars that all form roughly together in the same cloud, same molecular cloud. Now, going back to our solar nebula theory, is that a question?
Oh yeah, I was just gonna say, wait, if they say that there's like a shock wave, the only thing I don't understand is where that shock wave even came from.
Where it comes from is an important thing. And let's hold on to that because we will get to an answer on that when we talk about the Milky Way galaxy.
Oh, okay.
So it is something that's going to come up.
Sure.
But it's really important because if you don't have anything started, what do you got?
Yeah.
Magic.
How did that start?
What?
How did the first?
Yeah, how did the first one start? And so that's going to be an important thing we'll talk about with galaxies. So, solar nebula theory starts with a gas cloud. So it's showing a gas cloud here, 5,000 AU. What does 5,000 AU mean to you?
5,000, like from Earth to the sun?
Yeah, it's 5,000 times the distance from the Earth to the sun. If we compare that to our solar system, well, obviously it's 1 AU from the Earth to the sun. It's about 10 to get out to Jupiter, and you get out to the farthest extents of the galaxy, and you're talking about 1,000 astronomical units to the farthest extents. And so this is a bit larger than the entire size of the solar system, but it's in that ballpark. So you have this thing, and then something causes it to get close together, so gravity takes over, and things start falling in. Things start falling in because you're always going to have some random overall rotation. you end up rotating in one direction. Stuff is falling in. Well, the direction that stuff is falling in, stuff blowing out is going to meet resistance. But if you go up or down, not in the plane in which stuff is falling in because it's already flattened, then the stuff can get out. So you tend to have jets of stuff being blown away by the forming star coming along the axis of the disk. So the solar system going around like this, it would have jets going up and down like that. And then in the end, you form your star system with a star at the center. So that is our understanding of how stars form. So we should be able to find evidence. Remember the whole scientific method. Notice something interesting. Something interesting would be, in this case, we appear to have a lot of stars out there. Where did they come from? Hypothesis, the idea I just explained, and then we look for predictions that it can answer. So we're going to look for things that show those jets. And here we have a picture of a single object, a protostar that has a forming star. It's called a Herbig-Haro object because these two gentlemen, Mr. Herbig and Mr. Haro, were the first ones to study and explain these things, where you have jets of gas coming out of the protostar. So here you have a protostar, and its disk is going to be right here, so you don't have any light coming out along the disk because it's being blocked by all of that dust. You have infrared radiation coming out from above and below, and then you have a jet shooting up. And these are 5-year, actually not 5-year, 3-year, I guess. It says somewhere here, I thought it said like 5, but it's a total of 5 years, okay. Total 5 years between them. I read this a little too quickly. I thought it was 5 years for each picture. But you have sequential steps in a 5-year period, which you can read by the numbers. And you can see subtle changes in what it looks like. Every couple months, you'll have something come out of here. So it's kind of like a machine gun that shoots once every couple months. Shoots out a bunch of material, gas, and stuff. And so we have evidence here that matches a prediction of the hypothesis. We can't go do experiment stars. So you can't just go conduct an experiment to test your hypothesis on star formation. But what you can do is you have a hypothesis that makes predictions about what you should find, and then you go study out there. And if you find the stuff that your hypothesis predicts, then you consider that a confirmation of that prediction. Are you done? What do? You test again and again and again. So you look for more types of things. So this is just one type of thing that astronomers are going to look for. Those evaporating gas globules we saw, another type of thing they look for. Here's some other pictures of Herbig-Haro objects. This one here is Herbig-Haro 1 and Herbig-Haro 2. I'm pretty sure that's the first pair that Herbig and Haro studied. And you have, in this case, somewhere here in between is where the star is, and it's blowing stuff out. And then when it hits another cloud, that's where you have the stuff that lights up. The picture on top, HH47, okay, HH stands for Herbig-Haro. It says that the star is somewhere around here, or maybe here. You know, it just seems my sense of symmetry says that the star should be at least here, if not here. But the text says it's over here, and I'm just going to have to believe it. It's blowing material out, and you see the signs that you have a forming star. And I'll stop here. Our last picture of protostars. I should have mentioned the T-Tauri object. T-Tauri objects are a star that is just at the end of its formation. So it's going from protostar to star. Protostar is, you have collapsing stuff, it has a dust cocoon. It's warming up, but it's not yet undergoing nuclear fusion. So if it's not undergoing nuclear fusion, it's not going to be super hot. So it's going to be giving off infrared radiation. Because of all the cloud, you're not going to see that infrared radiation for the most part. So that's a T-Tauri object. Once it starts fusion, then you have a big outward explosion because all of a sudden there's a lot of energy coming out where there wasn't before. And when you start fusion, it's going to blow away that cloud, and then you can actually see it. So that's when it becomes a star, when it blows the stuff away. So these are pictures where we're looking somewhat side on. So here it's definitely side on. You can see the disk where it's blocking light. These are looking on them, looking down the axis of rotation. So you have the stuff would be shooting out like this, and you have all the cloud around it. So these are images to show what we believe forming stars, what we believe are forming stars, things that confirm the theory. All right, we'll end here. Sorry, I'm a minute over. I'll see you for lab tomorrow. Pray for good weather.
So snow, right?
That would be it.